The Air and Space Museum is very pleased to have two game-changing aerobatic airplanes in the collection. One of them is the Pitts Special, the S-1S, which has symmetrical airfoils. It's a biplane. It's one of the exciting planes to come in the post-war era. It's a much smaller plane than the aircraft that were used prior to World War II for aerobatics. They were much larger and had large radial engines. The Pitts is a tiny, nimble aircraft based on the flat, horizontally opposed engine. And it's much smaller, the wings are smaller, and it just has an extremely high roll rate and is very nimble. The second one that we have is the Extra 260. The Extra 260 is based on the emerging monoplanes of the 1980s that are very strong aircraft, structurally strong. They have symmetrical airfoils that allow you to fly straight and level, upright, or to invert the aircraft. And then they allow you, because of their strength, because you can put very strong engines on, you can pull the plane and fly straight up and then do your hammerhead stalls and all these different active high G maneuvers that are very important for competition and very exciting for airshow audiences to watch.
When we see depictions of dogfighting in the movies, or training exercises that the military conducts, we get the impression that an extremely high level of skill is required of a pilot to outmaneuver his or her opponent in air-to-air combat. This is absolutely true. However, it's important to recognize that this skill is not just manual dexterity with the control stick, an ability to sustain high G forces, and acute perception of what the opponent is attempting to do. All of those things are required. But there's something else. A pilot must have a clear understanding of the performance of his or her aircraft, as well as the performance capabilities of the opposing aircraft. There are some physics-based limitations on what an aircraft can do, and it's critical for safety of flight and for optimizing competitive advantage in a dogfight to be intimately familiar with these performance characteristics. So in this lecture, we'll discuss the physics behind maneuvering flight. These basic principles govern all maneuvering flight, and we'll see how fundamental properties of the aircraft design influence maneuvering performance. We'll begin by considering a steady, level turn. It turns out that turn performance is the key factor that limits the maneuverability of an airplane. So this is a critical starting point for studying aircraft maneuverability. The key performance metrics that we care about for a level turn are the radius of the turn rate, and the load factor. First, let's consider a simple model of our aircraft in a turn. As an aircraft turns by banking its wings, which tilts the lift vector a bit in the horizontal direction. If the turn is perfectly coordinated with both aileron and rudder, the axis of the aircraft is tangential to the curved flight path and there is no side force acting on the aircraft. We can take the lift vector and break it up into vertical and horizontal components, and we'll apply Newton's second law, stating that force is equal to mass times acceleration, separately to the vertical and horizontal directions. Since the aircraft is in level flight, there is no acceleration in the vertical direction, and all of the forces in the vertical direction must be balanced. So the vertical component of the lift vector, lift times the cosine of the bank angle, must be equal to the weight in order to maintain level flight conditions. Now, the horizontal component of lift induces a constant radial acceleration that maintains the aircraft on a curved path. So the right-hand side is non-zero. The force is the horizontal component of lift, mass is equal to weight divided by gravity, and the radial acceleration is the square of the flight speed divided by the turn radius. Now, we simply take the first equation and substitute it in for weight in the second equation and solve for the turn radius. Here we see some interesting properties of a turn. The radius of the turn decreases as the bank angle increases, which agrees with our intuition. A steeper bank angle ought to produce a tighter turn. Also, the turn radius increases with the square of the airspeed. This is a very large effect. To gain an appreciation of the magnitude of this effect, let's consider a small Cessna 172 flying at 100 knots compared to an SR-71 at Mach 3.5. When the Cessna is in a turn with a modest bank angle of 30 degrees at 100 knots airspeed, the turn radius is around 1,500 feet, or 0.3 of a mile. In contrast, when the SR-71 turns with the same bank angle, but at Mach 3.5, the turn radius is 121 miles. This would be a truly massive turn. For example, if a pilot flying the SR-71 in a southeasterly direction over Cleveland decided to do a 180-degree turn, the center of the turn would be over Columbus, and the turn would be complete over Cincinnati. The SR-71 would cover the entire state of Ohio for this 180-degree turn. So we see that the flight speed can have a dramatic impact on the turn radius. If a tight turning radius is desired, which is the case for military aircraft in a dogfight, then it is best to slow down. Let's now consider the turn rate, which is related to how long it will take for the aircraft to complete a given change of heading. The flight speed of the aircraft along a circular path is equal to the product of the angular speed, omega, and the turn radius. So solving for angular speed, we see that the turn rate is equal to airspeed divided by the turn radius. If we bring in our relationship for the turn radius and substitute, we see that the turn rate is equal to gravity times the tangent of the bank angle divided by airspeed. A higher turn rate will result from lower airspeed and higher bank angle, which again agrees with our intuition. Now, there are two primary limitations on the turn performance of an airplane. One is aerodynamic stall, and the other is the maximum load that can be sustained by the structure. We'll take a look at each of these limitations in detail. First, let's look at the limit of aerodynamic stall. Coming back to our equation of motion in the vertical direction, we can solve for the bank angle for a level turn. This equation must be satisfied if level flight is to be maintained. A particular aircraft flight condition will be defined by the wing loading, airspeed, and altitude, which determines density. So a pilot pulling into a steeper turn with a level flight path will have to increase the lift coefficient. However, we fully recognize that there is a maximum lift coefficient, so maximum lift coefficient will dictate a maximum bank angle before stall occurs. For example, a typical aircraft with a wing loading of 15 pounds per square foot, flying at sea level at an airspeed of 100 knots, with a maximum lift coefficient of 1.5, will have a maximum bank angle of 67 degrees. Any attempt at a bank angle beyond this will stall the aircraft. This leads to some interesting consequences for safety of flight. For example, it's possible to make a one-way flight into a canyon or a mountain valley. A pilot can easily and unwittingly fly into a closed canyon where there is no possible way to fly back out. This happens when the climb performance of the airplane is insufficient to climb up and over the canyon walls, and if the canyon is tight enough, the required bank angle to do a 180-degree turn while clearing the canyon walls could lead to a stall. So no matter what the skill level of the pilot is, there are certain scenarios where the aircraft cannot safely escape. However, this level of danger may not be readily apparent to an untrained pilot. For this reason, pilots flying at low level in mountainous terrain are often encouraged to take specific training on mountain flying in order to prevent such dangerous scenarios. The problem of aerodynamic stall in a turn is also one of the biggest causes of general aviation accidents in the airport environment. This event is generally referred to as a loss of control, but that term tends to mask the underlying cause of this event. Most often, loss of control occurs when a pilot is making a turn to align with the final approach of a runway. Aircraft often fly a pattern with respect to the runway, particularly when the aircraft is approaching the airport from the opposite direction of the desired landing flight path. The pattern helps organize the traffic flow in the airport environment, particularly for airfields where there is no control tower to coordinate the flight activity. A pilot will enter the downwind leg of the pattern, which is parallel to and offset from the runway. Then the pilot turns 90 degrees from downwind to the base leg, which is a short flight segment that connects the downwind leg to the final approach. Then, after the short base leg, the pilot again turns 90 degrees in the same direction to get aligned with the final approach to the runway. Now, the desired runway is almost always selected such that the headwind is maximized on final approach. This allows the aircraft to minimize its ground speed for a given approach speed. If an aircraft were to land with a tailwind instead, then the ground speed would be the sum of the approach speed and the wind speed, resulting in a much higher touchdown speed relative to the ground and a longer ground roll. The loss of control situation becomes particularly significant when there is a strong crosswind relative to the runway, which forms a tailwind on the base leg. This tailwind will move the aircraft very fast relative to the ground on the base leg, and the pilot can easily miss the timing of the turn from base to final. This late turn would cause the aircraft to overshoot the final approach course. In an effort to turn the aircraft around quickly to align with the runway, the pilot may put the aircraft into a steep bank. And the steep bank is where the trouble is most often encountered. The aircraft is already flying slowly, so it has a diminished stall margin. Then the steep bank requires more lift to keep the aircraft from descending rapidly. The aircraft is close to the ground, and the pilot right away perceives the descent, leading to a pullback on the stick. This, of course, increases the lift, but only to the point of stall. If a stall occurs during the turn from base to final, then the pilot has very little room to recover. The aircraft is only a few hundred feet above the ground at this point, and there just isn't time to initiate a proper stall recovery. The changes in the stall margin can be significant. Let's say that the normal speed for final approach for an airplane with flaps deployed is 78 knots, or about 90 miles per hour, and the stall speed is 61 knots. The load factor scales with the bank angle. A 30-degree bank gives a load factor of 1.15, or 15% more lift in level flight. A 45-degree bank gives a load factor of 1.41, and a 60-degree bank will double the lift. So when we factor that into the lift equation, the stall speed goes up by 7.5% for a 30-degree bank and by 19% for a 45-degree bank. And for a 60-degree bank, the stall speed goes up by 41%, bringing that 61-knot stall speed all the way up to 86 knots. So we quickly see that an aircraft flying with flaps deployed at the recommended approach speed will put the aircraft into a stall if put into a level turn with a bank angle of 60 degrees. And if the pilot happens to be flying just a bit slower than the recommended approach speed, then the stall margin is reduced even further, meaning that a less steep turn will still result in a stall. When a pilot is attempting to overturn the aircraft, excessive rudder is sometimes applied in an attempt to nose the aircraft around the turn. This results in a slower relative airspeed over the wing on the inside, which would result in that wing stalling first. An asymmetric stall quickly leads to the development of a spin, which would quickly take the aircraft into the ground. I've experienced firsthand the fatal temptation to overcorrect a late turn. I recall one particular instance where I had a very strong tailwind while on the base leg of my pattern. My main thought was looking ahead to how I would fight the crosswind and come in for a successful flare and landing. But secondary to that, I was thinking ahead, trying to anticipate the effects of the wind on my base leg and to initiate my base to final turn early. Still, even with this thinking ahead, my turn left me on a path to blow past the final approach course. There was a strong urge to tighten my turn with a steeper bank angle, but thankfully I kept it to a reasonable bank of no more than 30 degrees or so. And holding that limitation, my late turn blew me off course. The only reasonable thing to do at that point was to throttle up and go around. It can be frustrating to go around since pilots sometimes get fixated on bringing the plane down for a landing, but a go around was the safe thing to do. So loss of control, which is really a turning stall, has remained one of the most persistent safety challenges in general aviation. Okay, let's come back to our discussion of the limitations on turn performance. We've been discussing limitations of aerodynamic stall. We can summarize that limitation with the following connected ideas. 1. The aircraft must produce extra lift in order to sustain the weight in a level turn and provide the radial acceleration needed to turn the aircraft. 2. The extra lift must come from an increase in the lift coefficient. 3. The tighter the turn, the steeper the bank angle must be, and the higher the lift coefficient must be in order to produce the extra lift. And 4. The lift coefficient has a limit defined by aerodynamic stall, which ultimately limits the turn performance of an aircraft. Now, let's consider the second key physical limitation to an aircraft's turn performance: the maximum load carrying capacity of the aircraft structure. We discussed aircraft structures at length in Lecture 9. A helpful tool to describe the magnitude of the structural loading is termed the load factor, which is simply the ratio of lift to weight. Since lift equals weight in straight and level flight, the load factor there is unity. But in a turn, the lift must exceed the weight in order to sustain the turn, and n rises above 1. The load factor is expressed in units of g's, or a multiple of standard gravitational acceleration. Now, Newton's second law, applied to the vertical direction of an aircraft in turning flight, indicates that weight is equal to lift times the cosine of the bank angle. When we apply this to the definition of load factor, we see that there is a direct relationship between load factor and bank angle. N is inversely proportional to the cosine of the bank angle. So as bank angle increases, the load factor also increases. We can use this definition of load factor to rewrite our equations for turn radius and turn rate. Now, with these expressions, we see that turn radius decreases as the load factor goes up, and turn rate increases as the load factor goes up. So a higher load factor provides a tighter turn. We commonly think of load factor as pulling G's. This causes the pilot and any passengers to be pressed down in their seats, feeling heavier than normal. A 2G maneuver would make everyone feel twice as heavy. A 2G maneuver would place twice as much loading on the aircraft's structure. At a certain point, defined by the aircraft design, the structure would not be able to sustain any further loading without failure. For small general aviation aircraft, this load factor limit is typically close to 4 or 5 Gs, while for military aircraft, the maximum structural limit can be much higher. In fact, the limit load factor for military aircraft is typically set not by the aircraft, but by what the pilot can sustain. A typical well-trained military pilot can sustain about 9 Gs before blacking out. It is also important to recognize that an aircraft can sustain negative Gs as well. This results when the acceleration is acting in the direction opposite of gravity, causing everyone and everything in the aircraft to be pushed upward. Negative Gs are routinely encountered in aerobatic flight and dogfighting when a pilot pushes the nose down, creating a curved flight path towards the ground. In this case, the radial acceleration vector is oriented nearly opposite of the gravitational vector. In fact, a pilot can maneuver the aircraft such that the radial acceleration of a turn exactly opposes the gravitational acceleration, leading to 0 G. In this case, everything inside the aircraft would be weightless. This type of maneuver is inherently transient, but a skillful pilot can extend the period of weightlessness for a reasonable length of time. In fact, for an extended period of weightlessness, the pilot would need to put the aircraft into a parabolic trajectory during the pitchover maneuver and ensure that the thrust equals the drag throughout the maneuver. Not every aircraft can accomplish this maneuver, since sufficient thrust is required to power through the climb of the parabola. This type of piloting can achieve up to about half a minute of weightlessness, but each segment of 0 G must be followed by a pull-up maneuver that has positive Gs of around 2. This type of flying was actually how the space scenes in the movie Apollo 13 were filmed. They fit the set and actors inside a KC-135A and flew hundreds of parabolic maneuvers. Each individual 2 to 3 hour flight would have 30 to 40 parabolic maneuvers. With this continuous up and down motion, a significant number of passengers would encounter nausea, leading to the aircraft's nickname, the Vomit Comet. Despite the unpleasantness of the experience for some, these parabolic maneuvers are the only way to truly produce weightlessness on a large scale without going to space. So we see that an aircraft can pull positive Gs, negative Gs, or even 0 G under controlled circumstances. And an aircraft will have a load factor limit that is based on structural limitations. The two limitations on turn performance, stall and load limit, are commonly plotted in a way to delineate the flight envelope. The aircraft's load factor is plotted against the airspeed to depict the maneuvering performance envelope. This is called the VN diagram. On the right side of the VN diagram are curved lines that represent the stall limits. There are lines for both positive and negative stall, since a wing will also have stall characteristics at a specific negative angle of attack. So at low speeds, the turn performance is limited by the stall characteristics of the wing. At a certain load factor, the wing will stall. But at higher speeds, stall no longer limits the load factor, and structural limits rule. The specific value of load factor depends on the certification category of the aircraft. Small general aviation aircraft and commercial transport aircraft will have lower load factor limits than military fighter jets, for example. The point where the stall limit and the structural limit meet is an interesting point on the diagram. Recall the trends on turn performance that we discussed a few minutes ago. Turn performance is optimized by simultaneously lowering the airspeed and increasing the bank angle to pull as many Gs as possible. When we merge these two trends, we see that we want to push towards the upper left direction of the VN diagram as much as possible. This takes us to the corner where the stall and load limit lines meet. At this flight condition, the aircraft will be able to achieve optimum turn performance. Maneuvering at this airspeed will allow the pilot to pull the maximum Gs allowed by the load limit and fly as slowly as possible without stalling the wing. Any slower speed at this load factor would stall. The maneuver speed, as we call it, is a very important speed limit for a pilot to know. It's kind of like a safety feature. If an aircraft begins to fly into severe turbulence, there's a significant risk that the unsteady gusting winds could induce enough structural load to exceed the load factor limit. But if the pilot decelerates the aircraft to the maneuver speed or below, then a turbulent gust would cause the wing to stall before enough load could be applied to reach the structural failure limit. Another way to see the impact of stall and load limits on the turn performance is to plot the minimum turn radius, with lines for the stall limit and the load limit. We can see clearly that as the flight speed increases from very slow airspeed, the stall limit allows a dramatic reduction in the turn radius. And as speed decreases from very high airspeed, the load limit allows a gradually reducing turn radius. So for optimum turn radius, the pilot should fly at the airspeed where the two limit lines cross, which is the maneuver speed. A plot of the turn rate performance, which we want to maximize, also demonstrates an optimum condition at the maneuver speed, where the stall limit and load limit lines cross. At low speeds, the stall limit line gradually increases to higher turn rates, while at high speeds, the load limit will also gradually increase to allow a higher turn rate. So clearly, the maneuver speed is the airspeed that a pilot should fly for maximum maneuverable performance, and is the highest airspeed that a pilot should fly in severe turbulence. It's a very useful speed limit for a pilot to be aware of. Now there's one more limit on the VN diagram at high speed. There is a hard limit on the maximum speed due to the maximum dynamic pressure or aerodynamic load that can be sustained by the airframe. This establishes a never exceed speed, which we can think of as a red line speed. For many aircraft, it would be very easy to exceed the red line speed when the aircraft is in a dive. Let's now consider an aspect of aircraft design that has an impact on the maneuverability of an aircraft. Coming back to the definition of load factor, we see that the load factor is proportional to the air density, airspeed, and lift coefficient. All of these parameters are essentially set by the flight condition. However, in the denominator of the load factor, there is the wing loading, which is the ratio of weight to wing area. Since wing loading appears in the denominator of the load factor equation, we wish to minimize the wing loading in order to maximize the load factor for a given flight condition. In turn, maximized load factor will optimize the turn performance for that flight condition. Now, wing loading represents the load concentration per unit wing area, with units of pounds per square foot. An aircraft designer can select the value of wing loading in the design process. In fact, this is one of the most critical parameters for aircraft design. For maximum turn performance for a fighter aircraft, the designer can push the wing loading to lower values. However, there are other constraints on wing loading that would drive the designer to push towards higher wing loading. For example, efficient high-speed cruise flight demands higher wing loading. So an aircraft designer has to carefully weigh out the pros and cons of the performance implications of wing loading. There's one other trick that can be employed to manage the wing loading. If a fighter jet suddenly encounters an enemy aircraft and prepares to engage in a dogfight, the pilot can dump fuel overboard to reduce the weight of the aircraft. This will reduce the wing loading, which allows the pilot to maneuver more aggressively and pull more Gs. Taking a look at the VN diagram for an aircraft at two different weights, we see that the maximum load factor increases as the weight decreases, yet the speeds for maneuver remain the same. So all the pilot has to do is dump fuel as quickly as possible and engage in the dogfight at the same maneuver speed. Now, the very most important aspect of flight that a fighter pilot must manage in a dogfight is energy. A fighter aircraft's energy is comprised of kinetic energy and potential energy. The kinetic energy depends on the flight speed, while potential energy is based on the altitude of the aircraft. Due to the principle of conservation of energy, the aircraft's kinetic energy can be directly traded for potential, and vice versa. Very effective dogfighting maneuvers rely on expert management of energy and this energy trade-off. While a pilot can throttle up the engines in order to climb or accelerate, this takes time for the engines to spool up and for the action of increased thrust to increase the aircraft's energy. Energy management can be facilitated by a thorough understanding of the aircraft's performance characteristics. Fighter pilots often rely on energy diagrams for their aircraft and for that of their opponent. An energy diagram plots potential energy versus kinetic energy, usually in the form of altitude versus Mach number. If we plot contours of constant energy on this diagram, we can see how a pilot flying at low altitude and high speed can easily climb without adding any thrust by simply trading kinetic energy for potential energy in what is known as a zoom climb. This causes the aircraft to follow along a contour of constant energy until it reaches the new flight condition with higher altitude at a lower flight speed, but with the same overall energy. On this same diagram, we can plot contours of the specific excess power of the aircraft across this range of flight conditions. Now, the excess power will depend on the thrust characteristics of the engine at that condition and on the aerodynamic drag. In order to maximize the capability of the aircraft to increase its energy level, it's best for the aircraft to fly a profile that follows the locus of points where the specific excess power curves are tangent to the constant energy contours. In a sense, this guarantees that the aircraft is continually flying at the condition for maximum energy along a given contour of specific excess power. If we follow this approach, an interesting condition arises when a supersonic aircraft attempts to accelerate and climb to high-altitude supersonic flight as quickly as possible. The optimal schedule of flight conditions is a bit non-intuitive. The aircraft will climb and accelerate simultaneously, as we would expect. However, when this particular fighter jet reaches sonic conditions, the optimal flight profile will actually take it on a zoom dive, where it accelerates on a descending profile. The overall energy increases as the kinetic energy builds rapidly, and the aircraft accelerates rapidly through the transonic drag rise into the supersonic regime. At a certain supersonic Mach number, the aircraft resumes its accelerating climb, this time with a much higher Mach number. This could be a very useful profile for an aircraft to fly when the pilot needs to intercept an enemy aircraft as rapidly as possible. So, aerobatic flight and dogfighting are all about energy management. Some interesting maneuvers come out of the concept of energy management. For example, the hammerhead is an aerobatic maneuver where the aircraft does a pull-up maneuver, pulling Gs until it is climbing straight up. In this configuration, the aircraft's potential energy will be increasing very rapidly, but if the thrust-to-weight ratio for the aircraft is less than 1, then the kinetic energy must decrease during this straight-up climb. As the kinetic energy decays to a very low airspeed, the pilot kicks the rudder while there is still just enough airflow over the control surfaces to retain flight control, and the aircraft performs a 180-degree turn about its yaw axis. As the aircraft dives straight down, it rapidly exchanges that potential energy for kinetic energy. A pilot executing a hammerhead maneuver must be careful to kick the rudder over before the airspeed completely bleeds off. If the pilot waits too long, the aircraft will start falling backwards, resulting in reversed flow over the wing and the control surfaces. This phenomenon, referred to as a tail slide, can lead to unexpected aerodynamic moments resulting from control inputs. Some airshow pilots will intentionally venture into a tail slide, which resembles chaotic and out-of-control motion of the aircraft until recovery is achieved. Another interesting aerobatic maneuver is the barrel roll. If performed properly, the aircraft can roll about an axis parallel to its flight path. A barrel roll is not the same as an aileron roll, where the aircraft rolls about its own longitudinal axis. Instead, the barrel roll is more of a spiral or a helical motion, and we can imagine that the aircraft wheels are continually riding along the inside of a very large barrel. Let's take a look at how a pilot can execute a barrel roll in his flight simulator. The maneuver is started from level flight by pulling back a little bit into a brief climb. Then the ailerons are deflected to turn the aircraft up and over the top. At the top of the barrel roll, the aircraft's path is oriented at 90 degrees to the original flight path. But then, as the roll is carried around through the spiral, the aircraft's nose again gets aligned with the original direction of flight. The barrel roll can be a very useful maneuver in dogfighting, since the forward motion of the aircraft is retarded while the airspeed remains constant. This can cause a following aircraft to overshoot the aircraft executing the barrel roll, handing off the advantage to the pilot who executed the roll. It's also possible to execute a 1G barrel roll, such that the aircraft and its occupants feel 1G throughout the maneuver. Appropriate pitch must be applied to produce the acceleration needed to counteract gravity while in an inverted flight, but that acceleration must be relaxed by the time the aircraft rolls back to a wings level condition. The famous test pilot Bob Hoover was known to do a 1G barrel roll while pouring a glass of iced tea, just to prove that 1G was maintained throughout the maneuver. What a stunt by an amazing pilot. So let's summarize. The maneuverability of an aircraft depends significantly on the airspeed and the load factor. Limiting conditions for optimized turning flight are the structural limit and aerodynamic stall. Moreover, the stall speed creeps up as the aircraft is in a turn, leading to many fatal loss of control accidents in aviation. And finally, dogfighting in a military aircraft is all about energy management, where kinetic and potential energy can be traded in interesting ways to surprise the opponent.